All right, line P5, learning task 3, high voltage transformer calculations. We're not going to go through how to do the actual connections, Y to delta, etc. We covered that in P3. The high voltage transformer connections are going to be done in an identical manner. You're going to start with the A side first. You're going to do the A at 32 neutral. We'll just draw through the first couple of steps. To neutral, we're going to go off at 30 degrees, and then to B, we're going to go off at 60 degrees, and then we start with the high side, and then we draw out all the rest of the low side, the C, and then we just match our transformer windings to form the secondary. All of that is going to be done the exact same, so we're not going to go through any of that inside here. We're just going to go and look at the transformer calculations that we're going to have when we are dealing with a high voltage transformer. And we're going to go through a bunch of our common calculations. The first one that we're going to go and have is where we have got a primary that is going to be a delta, a relatively low value delta, 13.8 kV. It's high for us, but for transmission and generation, this would be considered low. We are going to go and create it as 13.8, and then we're going to go and transform it to a high voltage Y on the output so that we can go and get our transmission distances up. And there's a couple big benefits to the way that we go and do this. First of all, if we go and create a delta type of bank, then what we're going to be able to do is we are going to be able to go and take large amounts of current, send it into the transformer bank, and split it across the phase windings. Our phase value of current is going to be less than our line value of current, which means that these windings that we see over here don't have to be nearly as big as what they would have to be if they had to carry the entire line value of current that they would have to have. Allows for a reduction in the cross-section area of the windings, so the winding copper. It also means that the windings are going to be closer together, which means that we are going to be able to go and get much better flux linkage. We're going to have less losses inside of there. And it means that our transformer is going to be able to be a bit smaller because we've got smaller windings that are going to be placed inside of here. We then transform through the magic of magnetic flux over to our high voltage Y side. The Y side also has a couple of our main benefits that we have when we look at this thing. The big thing for our Y is that our phase values of winding over here, our phase windings, are not nearly going to be at the same voltage values as what we would have going from line to line, which means that the insulation that goes around these is once again going to be a little bit thinner, and it's not going to be exposed to as high of a value of electrical stress. This is a benefit for us as well, because when we take a look at our phase insulation, if we can get away with thinner values of insulation around here, that means that then we can also once again place our windings closer together. We're going to go and have less losses off of them, etc. The other reason that we have is that when it comes to our actual terminations, where we are going to be taking each one of these out of the transformer bank onto the actual transformer itself, physically speaking, we are going to be able to go and have smaller bushings. Because we're at a phase value of voltage in comparison to ground, remember that can of the transformer is going to be grounded, we've only got to insulate for that value of voltage over there. So smaller bushings, less expensive components, shorter creepage distance, less chance of a flashover that we are going to go and have. That's our benefits to why we are doing this. So we're coming out of our dam where we're generating power. We're going to go and head into a delta side, create some flux, and then we are going to go and pass it out to a Y voltage side. Over here, they're going to give us these values. Delta to Y, we've got 13.8 line voltage produced by a generating station out to 250 kV. 50 kV, 250,000 volts over there. And then each of these transformers is going to be rated at 10 mega VA, 10 million VA that we are going to go and have for each of these. Okay, well, if we've got all of this over here, we can start to go and make our transformer calculations. First thing that we are going to go and take a look at is we're going to look at the voltage ratings of each of our windings. Once we know what our voltage ratings are, then we can go and take a look at the turns ratio and then our line-to-line voltage ratio. Let's start on the primary side, the side we're feeding power in. Well, on my primary side, we know that we are looking at a delta, and we know that E line is equal to my E phase for a delta. Therefore, for each of my windings inside of here, they're going to have to be able to withstand that same 13.8 kV that we're going to have across them. On our secondary side, we've got 250,000 volts. Now this is going to be a line-to-line value of voltage, which means that my phase value of voltage is going to be much smaller. I can actually erase that because that's down here. So we're going to go and say that my E phase is equal to my E line divided by root 3. We'll take that into our calculator over here, 250,000. I'm just going to go 250. I'm not even going to go drop it out of the thousands. I'm going to keep everything in K values, divide it by root 3, which gets me to a value of 144 kV, 144.37 kV that we will have for our value of voltage. This winding here, 144.3 kV. Now that we have those two, we can figure out the turns ratio of our transformers. Turns ratio is going to be relatively straightforward. Just center this calculator down here a little bit better. We're going to go and take my high side voltage, 144.3, over top of my low side voltage, 13.8. Since I've already got the 144.3, I'm just going to divide that by 13.8, which gets me to a value of 10.45 to 1 that we are going to go and have. In your book, they show you a different turns ratio. They're showing you the opposite or the inverse of what we would have over here. Don't worry so much about that one. It is a way you could go and write it, 0.0956 to 1, but it's much more common for your turns ratio to actually be your high side to your low side. So 10.45 or 10.46 to 1 that we will place in. TR 10 point, let me just do a point over here, 10.46 to 1. What is my actual line-to-line voltage ratio? Well, my line-to-line voltage ratio is going to be my 250 over top of my 13.8. So we'll just try that one. 250 divided by 13.8, which gets me to a value of 18.12 to 1. So my voltage ratio, 18.12 to 1. Okay, that covers off for our voltage over there. The next thing we're going to start looking at is going to be our VA and then our current. All right, in order to go and start our power, the first thing we're going to take a look at is going to be the ratings excuse me, of our individual transformers. And we see that our individual transformers each have a rating of 10 megaVA. So if I go and add up all three of those, 10 megaVA plus another 10 megaVA plus another 10 megaVA, I'm going to go and find out that my total is going to be 30 megaVA that I'm going to go and have for my overall bank. Now that we have that in there, what we can do is we can start figuring out our line values of current, and then from our line values of current, we can then drop down to our phase values of current that we are going to go and have. Let's start and find our line voltage, or sorry, our line current on the primary side, then we'll jump over to our line current on the secondary side. 30 megaVA. Now we can go punch this thing in all the way across. That's 30 megaVA divided by, and then we're going to do bracket our primary line voltage. Remember, primary is the side we're feeding in, not our high, so 13,800 times second root 3, like that. Gives us a value of 1,255 amps that we are going to go and have for our line value of current. Let's place that in onto our lines over here. 1,255 amps that we are going to go and have. We know that our primary is connected in this delta, which means that our phase value of current is going to be less because our line current is coming in and then it's splitting up across these two phases. We know that I phase is equal to, oops, sorry, I wrote an E there. I line divided by root 3. So we're going to go take our value that we have over here, 1255. We're just going to go and divide it by root 3, which gets us down to an individual phase current of 724.6 amps. So each of these windings is going to be carrying 724.6 amps through them. Going over to our high voltage side, same deal. We're going to go through the same steps there. 30 million divided by 250,000, that's our line value of voltage, times root 3, which gets us to a value of 69.28 amps. amps. This is going to be my line value of current, so we see that there's a very small amount of current that actually flows out over top of the line, 69.28 amps, that we're going to have flowing over top of it. And because we're connected in a Y, we know that whatever current that we are going to go and feed out has to all go through the phase as well. So therefore, each of my currents through the amps is going to be 69.28 amperes as well. Perfect. That covers all of our calculations. Once again, looking at the benefits that we have for these, we see that we're able to go and feed in a lot of power, a lot of current, 1255 amps, but we see that our individual windings are only going to have to be rated for 724. And on our high side over here, we see that we're bumping up to such a high value of voltage that we've only got a tiny amount of current that's traveling through it, which means that we're not going to have a lot of I squared R or IR losses. We also see that our primary phases only needs to be insulated to 150,000, roughly 144.3 kV, that we're going to need to insulate our high voltage windings as well as the actual high voltage bushings themselves. Okay, so we've done that one. The next one that we're going to go and move to is going to be for a step down high voltage transformer bank. And the step down is really going to go and be a dropping over from our high side back down to our low side over here. We are going to go and run through at the higher line value of voltage, but then we are going to go and increase the amount of current that we're going to go and feed out as we get through onto our secondary line. So this one over here, our figure number 2, is going to go and, oops, sorry, I have figure number 2 there. Delta to Y. Oh, yeah. I just did it off of the wrong drawing over there where we were feeding in as 13.8 and then we were feeding out. It's the second one that they're showing over here is a Y to delta, where they're going to go and jump up to a value of high voltage of 250,000. This one that they have over here is going to be a poor connection, because what we're doing is we're coming in on a Y, and then we're transforming over to go to a delta. And we're going to go and have a lot of losses off of that delta side over there. Not necessarily actually losses, but we're going to have a lot of, benefits that we would not get. Lost benefits, I guess, is the better word for what I'm trying to go and say. Because what we're going to have is we are going to have on our windings on the primary line here, we're going to go and have really thick windings, because all of my I line is going to be equal to my I phase that I'm going to go and have over here. So we're going to have thick, heavy copper coils through these ones over here. We're not going to really gain much of a benefit. We're dropping from 13.8 down to a smaller phase value of voltage, which isn't really going to give us a whole lot. And then going out on our secondary line over here, we are going to go and have only a tiny, tiny amount of current inside of here. So it's going to be amps are going to be small inside of here, but they're going to go and combine to form a slightly larger amperage over here on this line. But once again, it's not going to be a crazy, crazy amount of current that we are going to go and have out of here. It's going to be the same values that we are going to go and have, because it's the same transformers, 10 mega V8 that we're going to go and put out. The other thing that we're going to have issues with is that each of my lines is now going to be a fairly high voltage type of line, and my phase windings, my E line and my E phase, are going to go and be the exact same, which means that I'm going to have thicker insulation around each of these windings over here. I'm not going to go through all of the calculations for example number 2. You can go through the calculations off of these ones and go through and figure out exactly how they make the individual connections for each of these. Well, whatever. It's not going to take as long. I'm going to go through them anyways. It's just maybe better that I do. Never mind what I just said. Let's do these calculations. Okay, so this is going to be my poor connection or not effective. We'll take a look at how this thing is not effective. 13.8 kV primary line coming into this thing, and we are going to go and have 250,000 coming back out of this thing. The very first thing that I'm going to do with, I'm going to go through in a different order over here, is I'm going to go and start with my 10 mega VA transformers that I have 3 of, and I'm going to go and add 3 of them together. second, third, so that we can figure out our total kVA. Our total kVA is going to be 30 MVA, mega VA, that we're going to go and have for this entire system. And we see that our line values of voltage, 13.8 and 250, are the exact same as what we saw in the previous example, inside of example number 1. Which means that if I have got the same values of E line, 13.8, same values of mega VA, 30 mega VA, I should end up with the same values of current. Same with on the secondary over here, 30 mega VA, 250,000, and I should end up with the same values of current. We'll just punch through them real quick over here off of this one to make that proof. The first one that we're going to go and do is going to be, I could have just left that in there, but 30 mega VA, so 30 million, divided by my primary line voltage, so my inside 13,800, delete that, 13,800 times root 3. Make sure you're putting in those brackets once again, and we see that we are going to end up with that line current of 1255 amps. What's my phase current going to be? Well, in this case, I have got a Y over here, which means that my phase current is also going to have to be the same, 1255 amps that I'm going to go and have across it. Let's take a look on our secondary side. Same calculation. We're going to take our VA, 30 million, divided by, now my high side voltage, 250,000, times root 3, which is equal to 69.28 amps. So we see that we come out to the same values of current, 69.28 amps on my line. The big difference is that my high side is now a delta, which means that if I'm flowing 69 amps out of this thing, I'm going to have two smaller phase currents that are going to go and make that up. We can find that by just taking our line current, dividing it by root 3. So we're going to take this line current, divide it by second root 3, which gets me to a value of 40 amps. So my actual transformer high side winding is going to go and have 40 amps that's going to be going through it. Perfect. Let's take a look at our voltages that we are going to go and have. Well, if on my secondary over here, I have got 250,000 volts for my line value voltage, and if it's delta, that means that I'm also going to need to go and have 250 kV for my phase value of voltage. And on my primary, I know that my phase value of voltage is going to be root 3 less than my line-to-line value. So I'm going to take that 13.8, 13,800 volts, divided by root 3. Gets me to a value of 7.96 or 7.97 kV that we are going to go and have. kV that we're going to have. Taking a look at our turns ratio then, our turns ratio is going to be off of the volts that we have across from a phase to phase. So my turns ratio is going to be different than my voltage ratio. My voltage ratio is going to be the exact same as the other side over here. My high side, 250 kV over top of my low side, 13.8, which gets me to a 18.12 to 1. I'm going to drop that one right into here. 18.12 to 1. But my actual turns ratio is now going to be 250 over 7.67. 250K divided by 7.67K, which gets me to a value of 32.6. So I see I have to have a much larger turns ratio, 32.6 to 1. Okay, taking a look at this one, once again, the net losses that we have off of this thing, or the reason that we don't like this, is going to be because of what we see over here. Let me just erase a few things over here, and we'll just highlight through what we like. This is the good one over here. We'll just write that as good. Transformer connection. What we're seeing is we are seeing a couple of things. First of all, we're seeing on our high side, our phase voltage is low compared to the not effective. Our phase voltage is going to go and be high, which means that we have to have bigger bushings, better insulation, and just an overall harder to make type of connection. The other thing that we see over here on this one, the good one, is that my number of amps inside of my primary side, 724 over here, is relatively small compared to what I would have in my non-effective, where I would have to have 1255 amps. So I'm going to have a much bigger amount of copper that's going to be around there. As well, inside of the transformer construction itself, looking at these ones, 250,000 volts, I'm going to need to have a lot more wraps of insulation around the actual windings compared to this one that's only going to be 144 kV. This is why we prefer this one here, where we go delta in to a Y out when we are doing a step up. All right, let's take a look at a step down. The first one that we're going to take a look at is going to be our good type of connection, or our most common, most efficient type of connection. And it's going to go and be good for the exact same reasons. First of all, we are going to go and have on our high voltage, we will have a Y type of connection, which means that I'm going to have a high line to line, but my phase is always going to be lower, which means that I've got less insulation inside of the phase windings, as well as I'm going to be able to have smaller and cheaper and more sturdy bushings. The taller the bushing is, the less sturdy that thing is going to be, because it's just leverage off of the actual bushing itself. The other great benefit we have is because we're stepping down, and we're stepping down into a delta side over here, we are now going to be going and taking our current that we're sending out, and then we're going to add it up once it exits the transformer, not inside of the transformer. This means that we're going to go and have thinner copper on our high amperage side over here. Okay, let's go and take a look at our actual calculations. Once again, it's going to be a three-phase Y to delta, 250, and each transformer is rated at 10 mega VA. If we have got 10 mega VA that we are going to go and have for each of these, that means that our total bank capacity is going to go and be 30 mega VA that we are going to go and have. Which means that if I've got 30 mega VA, I'm going to be able to go and divide out by my primary value of voltage and root 3, which is going to get me to a primary line current. We have the exact same values as what we would have off of this side, only now we're doing the step down type of ratio, 69.28 that we're going to go and see over there. We'll go through the calculations one more time over here. 30 million on my high side, divide it by bracket 250,000, one there, times root 3. Which gets me to a value of 69.28 amps that I'm going to go and have on my high side line, 69.28 amps. And if I take a look, any sort of incoming line current has to go through the phase, therefore my phase is also going to be 69.28 amps. Going over to my low side is going to be done the same way, 30 million. 3 million divided by my low side line voltage, 13,800, times root 3, which is going to get me to a value of 1255 on my current, on my line. 1255 amps that I'm sending out on each line, which we know is going to be made up of smaller currents combining from each of these over here. And we can go and find the smaller currents by taking our 1255 and dividing it by root 3. So we'll just do that, 1255 divided by root 3, which gets me down to my individual phase current of 724. 724 amps that we are going to go and have through my individual phases. 700 amp winding, the copper size, compared to 1255 is going to be significantly less. Last thing that we have to do is we have to take a look at our values of voltage that we are going to go and have off of here. We see that on my secondary side that I am going to be a delta, which means my phase and my line are the same. So this is going to be 13,800 volts. On my high side, we're 250,000, so we're just going to be root 3 less than that. 250 divided by second root 3, which gets me down to 144 kV that we will have. We'll place that over here, 144 1,000 volts. We're doing a little bit of rounding, I get it, but it's because we've done these calculations a bunch of times already. It's a step down from what we had on our previous one. Turns ratio and voltage ratios are going to be the same as what we saw in our very first example, number 1. turns ratio is going to be 144,000 over 13.8, which when you do it is going to go and give you a turns ratio that is going to be 10.46 to 1. That's a colon there, 10.46 to 1. And my voltage ratio is just going to be the high side voltage over top of the low side voltage. So it's going to be the same 18.12 over 1 voltage ratio that we'll get out of this bank. This is our good, efficient bank. We once again could do things poorly if we go through a reverse over here. If I come in as a high voltage delta over here, I'm going to go and lose those benefits of having a lower phase voltage. I'm going to have windings that are going to be good for 250 kV. That's a lot. And then flowing out over here on my secondary line, I'm going to go and have to have, well, it's not necessarily going to be terrible. Depends whether we need a neutral or not on that one. But I am going to go and have all of my current, whatever I run out of the transformer on my lines, is going to have to come through my phases themselves. We'll go through these calculations as well. Once again, it is going to go and be 10 MVA that we will start with. For each of these, 10 MVA. And if 10 MVA and 3 transformers, that's going to get me to 30 MVA. 30 MVA. That 30 MVA, we're then going to be able to go and divide out by our primary values of voltage and our secondary values of voltage to go and figure out what we have for our line currents. 30 million divided by brackets, I'm going to put in the high side voltage, 250,000 times root 3, which is going to go and get me to a total of 69.28 amps. We see that the amps stay the same. 69.28 amps. And that's because 30 MVA is 30 MVA. And if we're only looking at it from the line side, if I were to ignore everything that was inside of one of these transformers and just look at it from the line side, we're always going to go and see, when we've got this 30 MVA and 250,000, that we're going to end up at that 69.28. Okay, so that's going to be my high side line current. If I take a look at my high side line current, I see I'm going to be feeding that into a delta where it's going to go and split up to become 2 smaller phase currents. So let's go and right away take this 69.28 and we're going to go and divide this thing down by root 3. Which is going to get me to a current of 40 amps inside of here. 40 amps, 69 to 40 amps is really not that much of a difference when it comes to transformer 1. It's only a small decrease in the size of the lines that we would need to have. Going over to my other side, I'm going to go and do the same calculations. 30 million divided by my low side voltage, line voltage, 8,000 times root 3, which is going to get me to a value of 1255 amps. And in this case, because it is a Y, we know that whatever we got for 1255 on our line, we would also have to have on our phase. So 1255 amps and 1255 amps that we're going to have over there. Last thing to look at is going to go and be what I need for my phase value of voltage over here. If we've got 13.8, we know we're going to have to be root 3 less than that for my phase value of voltage. So we'll take 13.8 divided by root 3, which is going to get me down to 7,967. 7,967 volts that we will have over here. Doing our voltage ratio and doing our turns ratio, our voltage ratio is going to be the same as what we've seen before, where we are going to go and have our line voltage over top of our phase voltage. So let's go and calculate that. Our line voltage over top of our line voltage, 250,000 over top of 13.8. 250 divided by 13.8. which gets me to a value of 18.12 to 1. So my voltage ratio stays the same. VR equals 18.12 to 1. My turns ratio is obviously going to have to be much greater because we're going from 250,000 all the way up to 7,967 over here. 250,000 on the high side divided by 7,000. What was that number there? 7967. 7967, which gets me to a value of 31.37. Equals turns ratio 31.37 to 1 that we are going to go and have over here. Perfect. Okay, that covers off all of our calculations that we are going to go and have. I do want to go and point out inside of your book under this one here, your calculation D that they're talking about, that they went the wrong direction with their calculation over there. And they went all the way up to 54.35. They multiplied it by root 3 instead of dividing it by root 3. Just disregard what they had inside there and don't worry about that 54.35. This is our turns ratio, the amount of high voltage, phase voltage over top of the amount of low voltage over here. This is correct. The book is wrong once again. All right, this is, like we said before, not effective. We don't want to go and see this connection. Because this connection, we see that we have ridiculously high values of phase voltage, which means large bushings, lots of insulation, etc. inside of there, as well as we have ridiculously large values of phase current, which means thick copper. It's not an effective connection. We much prefer that when we are stepping down, we come in a high side Y to a low side delta. Or if we do need a neutral, we might come in a high side Y to a low side Y.